We're live. Okay. Picking up where we left off, Bohr's theory of the hydrogen atom. I'm going to try to finish this by Thursday because I got homework due this weekend on chapter 6. If you look at just this, emission spectra, I don't think we've covered this, have we? We didn't do this part. Of atoms in the gas phase, we don't see a whole wavelength like you do with white light. You just see different lines. So they're called spectra, and if you look at something like hydrogen in the gas discharge tube, did I show you gas discharge tube? I think, didn't I bring it down here? No, I'll show you in lab today. And you treat it with a high voltage. The gas glows with a light, and if you go through a slit in a prism, you find out, like, for hydrogen gas, you only see certain wavelengths. You see something in a red, a blue, and a purple, and a violet. And if you look at the light from a hydrogen gas tube, it's kind of a purplish red. If you look at neon, it's an orange. If you look at mercury, it's kind of a real funky white. If you think of the old type fluorescent bulbs, which were mercury, fluorescent, which is why a lot of people don't like, in stores, women try on clothes in the dressing room, they have those fluorescent lights. They'd rather see how it looks in daylight. So different elements give different line spectra. I know it's hard to see there, but there's different line spectra depending on the element. And this is what was seen through something called the spectroscope. The spectroscope is, the previous slide was kind of a schematic of what a spectroscope looks like. So it's where you could actually burn elements, look at it through a prism, and you would see the lines. And if you can match up the lines, reference lines, you can identify what elements are in it. So this man named Rybert developed an equation that could calculate all the wavelengths of hydrogen spectral lines. So you have 1 over the wavelength is equal to the Rybert constant, that's the R with the infinity subscript, times 1 over N1 squared minus 1 over N2 squared. And lambda is the wavelength of the line in the spectrum. The R with the subscript of infinity is the Rybert constant. It's 1.09737316 times 10 to the 7th per meter. And N1 and N2 are positive integers where N2 is greater than N1. So we're going to elaborate on this one. If you think about the classical laws of physics, or classical physics, Newtonian physics, if you have an object orbiting another object, like an electron, it would radiate energy, and eventually it would spiral down into the nucleus and annihilate itself when it hit a proton. That's not good for matter. So obviously that doesn't happen. That's what happens if you have something in orbit, like satellites. You guys remember Skylab? Most of you probably don't. It's a space station. That eventually came back down to Earth through the orbits and burned up on the way in. So Bohr postulated that the electron in atomic hydrogen is allowed to occupy only certain orbits with specific energies. So the energies of the electron are quantized. So therefore, if they're in those allowed orbits, they don't radiate energy and they don't spin back into the nucleus. So we talked about quantized energies. Did we not? Yes, no, maybe. Okay. we'll talk about it again. So the energies that the electron in a hydrogen atom can possess are given by the energy is equal to minus 2.18 times 10 to the minus 18 joules over times 1 over n squared, where n is a positive integer, 1, 2, and 3. So the most negative value is when n is 1. Because 1 over 1 will give you the largest number. That corresponds to the most stable energy state. We call that the ground state, the lowest energy state of an atom. So, all right, I'm an electron. I'm on the ground state. I want to get up here. What do I need to get up there? Energy. Somebody's got to give me energy to get up here. So now I'm up here. So now I'm in a different allowed orbit. So I jump backwards, which is not going to do because I'm old, bones break, off the chair. Can I stop halfway down? No, I have to go all the way. So I had two choices. I can either be on the ground or on the chair. I can't be halfway in between. So those are two allowed states. So those are quantum levels. Either be here or I could be here, or if I'm going up on the desk, I can be here or here. So I can't stop in between. There's only certain allowed, like floors on an elevator. You can only stop on the floor. You can't stop halfway between. So if n is greater than 1, that's called an excited state. So you got to have energy to get up there. Okay? So the radius of each circular orbit, Bohr's model, depends on n squared. Thus, as n increases from 1 to 2 to 3, the orbits get bigger. So if I have a nucleus, one, two, three, the orbits get bigger. They're higher energy. So radiant energy absorbed by an electron causes the electron to move from the ground state, n is equal to 1, to an excited state. So I can have, here's my electron in the ground state. I add energy to it, I can get it up to here. So what happens when this relaxes and it goes back down to here? Loses energy, the equivalent amount that you put in. So it comes off as a photon. But wait, there's more. I went from 1 to 2. Well, I can go from 1 to 3. A lot more energy. And I can go back 3 back to 1. Or I can go from 3 to 2, and then from 2 to 1. Or I can go from 1 to 2, then 2 to 3. So there's different combinations I can make. And each one loses, when it relaxes, a different amount of energy. So it's a different amount of energy, different wavelengths. So we talked about photons being emitted when it goes back to the ground state. So doing all these mathematical calculations here, the final equation, change in the energy, going from one state to another, says it's minus 2.18 times 10 to the minus 18 joules times 1 over the final destination squared, NF squared, minus 1 over NI squared. So if I say it goes from 3 to 1, the final state would be 1 over 1 squared minus 1 over 3 squared times this. I can now calculate the energy. Then from the energy, I can calculate the frequency. Then from the frequency, I can calculate the wavelength. Because this gives me energy. And remember before, energy is equal to h nu, where h is Planck's constant. So if I have the energy for this equation, h is a constant, I can calculate the frequency. And remember, c is equal to the wavelength times the frequency. So if I have the frequency, c is a constant, the wavelength is equal to c over the frequency. Uh-oh. There we go. Now, people who will be watching this are going to say, what happened right here? Technical difficulties. So I could do it in 3 separate equations. What they did is they combined them all in one equation. So I get 1 over the wavelength is equal to 2.18 times 10 to the minus 18th joules, divided by hc, so those Planck's constant, speed of light, times 1 over final n squared minus 1 over the initial n squared. So all I do is take these 3 equations and plug things together and mush them all together. So you got one final equation, so you don't have to do 3 different steps. It's very kind of them. So somebody actually did this for a lot of the, remember the different combinations? They come up with a different series. The Lyman series for hydrogen atoms is when the final state would be ground level, 1. So if you go from 2 to 1, 3 to 1, and 4 to 1, you get different energies at different wavelengths. They all are in the ultraviolet, so you can't see them. If you start where the final is in the second level up, and you go from 3 to 2, 4 to 2, 5 to 2, those are all visible in ultraviolet. Those are the ones we see. And then, of course, 3, go 4 to 3, 5 to 3, 6 to 3. And then the bracket. And those are in the infrared. So there's what you see. The Lyman series, you don't see the Balmer series, you see the arrows are colored. Those are the ones you see. And remember, we showed the line spectra of hydrogen, the reds, the green, the blue, and the violet. Those are the ones you see in the Balmer series. So again, we're talking about hydrogen atom. How many electrons? 1. Let's make a wild leap all the way up to helium. Now how many electrons do we have? 2. Well, guess what? How many different combinations can you make now with 2? It becomes a lot more complicated. And to do the math becomes a whole lot more complicated. We're not going to do that. Yay! So calculate the wavelength in nanometers of a photon emitted when an electron transitions from n equals 4 to n equals 2. So the initial n is 4, the final n is 2. Required constants is Planck's constant and the speed of light. So we go back to that equation. Put in, okay, we know the 2.18 times 10 to the minus 18. There's Planck's constant, there's the speed of light, times 1 over n squared minus 1 over 4 squared. And if you do all plug and chug math, you end up with 1 over the wavelength is equal to 2.055 times 10 to the 6th per meter. How do you figure out what the wavelength is? Well, you just flip it. So the wavelength is equal to 1 over 2.055 times 10 to the 6th meters. And if somebody can tell me what that is. I don't quite remember what that is.
6. Is it 1.866?
That sounds about right. So 4.87 times 10 to the minus 7 meters. Well, we usually talk about wavelength in what? Nanometers. To change that to nanometers, we're going to multiply it by 1.0 times 10 to the 9 nanometers per meter. 487 nanometers. So that's somewhere in the blue-purple region. Blue-violet. So even though that looks like a real hard equation, most of them are constants. All you got to do is plug in the two ends. And then remember at the end to get the wavelength, flip it. And then multiply it by 1 times 10 to the 9 to get into nanometers. And that's one of those equations, I'm sure when it first popped up on the screen, you're going, oh my God, where did that come from? But most of the numbers are given to you. Questions? Good. So now we're going to talk about wave properties of matter. So waves generated by plucking a guitar string are standing or stationary waves because they don't travel along the string. Now you probably did this when you were younger if you had a slinky. Remember slinkies? The metal ones, not the plastic ones. Or jump rope. People could stand at each end and you would shake it, and if you get just the right frequency, you get this wave that would just stand. Standing wave. Or now in the gyms they have these ropes that you do this. I don't know what they do that for, but they do it. So some points in a string are called nodes. They don't move at all. So the amplitude is 0. It's right at that midline, and we'll see some examples. So there's a node at each end, and there may be one or more nodes in the middle. So if you look at plucking a guitar string, you see where n is 1. We have a node at each end, nothing in the middle. It's a half wavelength. When n is 2, we have a node at each end, and we have 1 in the middle. And where n is 3, we have a node at each end, and we have a node here and here. Well, his hypothesis, Mr. Broglie guy, an electron in an atom behaves like a standing wave. Only certain wavelengths are allowed. And it doesn't show up well here, but it should be relationship between the circumference of allowed orbit, 2 pi r, should be pi, question mark, and the wavelength lambda, the electron is given by 2 pi r is equal to n times the wavelength, where n is a positive integer. So n is 3 is allowed, n is 5 is allowed, n is 3 1/3, not allowed. It's got to be a positive whole integer. You don't need, pardon?
Is that why it's broken?
Yes. And because only certain values of n are allowed, then only certain values of the size of the orbit are allowed. Because n times the wavelength is equal to 2 pi r. So n can only be 1, 2, 3, and 4. You can only have certain values for 2 pi r. So it must be quantized. So the orbits have to be certain levels. You can't have anything in between. So his reasoning, you don't have to write down all these equations. So waves can behave like particles, and particles can behave like waves. They have to deal with the duality nature of light. So his equation was wavelength is h over mu, where m is mass, mu is velocity. I'm not going to really get into that, but just walking you through it. So if you calculate the wavelength using that equation, it's called the de Broglie wavelength. If you calculate the mass using that equation, it's called the de Broglie mass. And then kind of skip that because we don't really need to do that. So James Thomson actually directed a beam of electrons. Now we know electrons are particles because we have a weight tool, a little. Through gold foil, he got this series of concentric rings, which looks exactly what you get from an X-ray pattern. Now X-rays are waves. So he demonstrated that electrons or particles have wave-like properties. They behave like waves. So once again, we're seeing that light or electrons can have a wave-like and particle-like property. So now we're getting more closer to the atom. So we're going to talk about the uncertainty principle. And the uncertainty principle states, what? What did you say? Exactly. That's exactly right. I don't know. The uncertainty principle is I don't know. How many people are always afraid to answer? What that means is, if you have a particle that's moving, you can either know its speed or its location. You can't know both. Think of you're standing on I-40, exit 312. Car goes whizzing by 120 miles an hour. You call the highway patrol and say, where's this car going 120 miles an hour? Where is it? Exit 312. Well, by the time you say exit 312, it's not at exit 312. It's down the road. Same car goes by. You happen to take a picture of it right by the sign that says exit 312. So you look at the picture. Where's the car? Exit 312. How fast is it going? Latest idea, just got a picture of a car. That's what it says. So it's the Heisenberg uncertainty principle. Yes, Heisenberg from Breaking Bad, that's where that came from. Is it possible to know simultaneously both the momentum, p, and the position x of a particle with certainty? We can state that as the change in the location, the position x, times the change in the momentum, p, is greater than equal to h over 4 pi r. Or 4 pi, rather, 4 pi. So if you have a particle with a certain mass, put the mass term in there, the mass times the change in velocity. And the changes are the uncertainties. What that means is the more precise you know the location of a particle, the less precise you know its speed. And the more precise you know its speed, the less precise you know its location. So how does that figure with the atom? So here you have an electron in a hydrogen atom, has a velocity of 5 times 10 to the 6 meters per second. Plus or minus should be 1.1%. Using an uncertainty principle, calculate the minimum uncertainty in the position of an electron. The size of a hydrogen atom is 1 angstrom. That's the abbreviation for angstrom, A with the little circle above it. So here we're doing the mass of electron, 9.11 times 10 to the minus 31 kilograms, and Planck's constant. So the change in the momentum would be, that's 1%, 0.01 times 5 times 10 to the 6th. We know the change in the velocity, plus or minus, would be 5 times 10 to the 4th meters per second. So delta x, rearrange that uncertainty equation, figure out delta x. Delta x is greater than or equal to 1 times 10 to the minus 9th meters. So the minimum uncertainty in the position is 1 times 10 to the minus 9th meters, or 10 angstrom. So if you tell me, I ask you where, or you ask me where the electron is in a hydrogen atom, I can only tell you with a certainty that is somewhere 10 times larger than the size of the atom. So I can't be any more certain where that electron is than 10 times, an area 10 times of where that the size of the atom. It'd be like somebody calling me and saying, "Where are you?" Of course, I know you're here in this classroom. And I respond, "Well, she's in Smithfield." Oh, yeah. Big area. So that leads us to the Schrodinger equation. Anybody ever seen the Schrodinger wave equation? Google it sometime. It'll make your hair stand on end. We had to do this in high school. Requires advanced calculus to solve. And apparently we're not going to discuss it because it says we're not going to discuss it. However, we are going to talk about it. So, incorporates both particle behavior in terms of mass and wave behavior in terms of something called a wave function, for psi, and it's the wrong symbol there. Psi actually looks like a little trident. Seeing that as a psi symbol for a psi function, which depends on the location in space of the system, such as an electron. So the wave function has no direct meaning, physical meaning. The probability of finding an electron in a certain region of space is proportional to the square of the wave function. And it's this. If you look at the Schrodinger wave equation, it's a whole big long equation with a bunch of those in there. So basically it says, figures out the probability of where to find an electron. So you have a room, empty room, light bulb on in the middle of the ceiling. You're about to go in a room, and I tell you there's a moth in the room. Where's the moth? By the light bulb. How many people have ever had a moth in their house? Do you ever walk in a room and you see it up on the wall? Not by the light bulb. You just told me it's going to be by the light bulb. So do you call Channel 11 News and say, "Hey, what's going on here? It's supposed to be by the light bulb. There's supposed to be some kind of freak of nature." No, but there's a high probability it's going to be by a light bulb. So that's what the Schrodinger wave equation tells you, the high probability of where the electron could be. Anybody hear Schrodinger's cat? You've heard of it? Schrodinger's cat. It's kind of, you might see it in philosophy, you see it in math. So you have a cat in a box, and depending on the scenario, the cat does something, like he releases poison gas or that. So you can open the box. Is the cat dead or alive? That's right. The answer is both. It's both dead and both alive. It's both dead and alive. Because it doesn't become dead or alive until you open the box and actually observe it.
It's also possible it couldn't be there at all.
So I don't want to go too far into that, but so we're talking about the quantum mechanical description of a hydrogen atom. So the Schrodinger equation specifies the possible energy states that the electron can occupy in a hydrogen atom and identifies the corresponding wave functions. So they're characterized by what we call quantum numbers, so which we can construct a comprehensive model of the hydrogen atom, and we use that to infer the other atoms. So here we see the nucleus with the electron density map around it. So for those of you who watch the Big Bang Theory, you know, in between your little segments, they show the atom rotating like this. That's completely wrong. Okay, electrons don't orbit around the nucleus, because an orbit is a two-dimensional thing. Planets orbit around the sun. Electrons, think of it as a cloud around the nucleus. Somewhere in that cloud. It's a three-dimensional structure. So here we see where it's dark, towards the middle, there's a high probability of finding the electron there. As you get farther and farther away, there's a lesser probability. Doesn't mean it can't be there, but it's a lesser probability. Just like when you walk into the room, there's a high probability the moth is going to be by the light bulb. Doesn't mean it can't be on the wall. It's just a lower probability. So we don't talk about atomic orbits, we talk about atomic orbitals. And the reason we use orbitals is because everybody was talking about orbits with Bohr's model, so when it came out with quantum mechanics, it was just easier to kind of just change it to orbitals. See, the orbital can be thought of as a wave function of an electron in an atom. So when we say an electron is in a certain orbital, what we're saying is it has a high probability of being in that location in space. Figured out by the Schrodinger wave equations. So atomic orbital has a characteristic energy as well as a characteristic distribution of its electron density. So we're going to talk about all the different orbitals. Quantum numbers. Well, what quantum numbers are essentially the address of an electron. So if you have a job, let's say, delivering pizzas, and you get a call to deliver pizza at NC State, one of the students, well, first of all, you get to NC State. Now you're there, you got to find where students live. You got to find the right dorm. So now you got the dorm, then you got to find the right floor. Now you're on the floor. Now you got to find the right. Now you got the door. You got to find the right person. So each additional thing gives you more specific information on where you're supposed to take that pizza. Unless you go in the bottom, and I'm there, and then I got pizza. Okay. So we're going to talk about these. 3 quantum numbers are required to describe the distribution of electron density in an atom. So these all come from the Schrodinger wave equation. The principal quantum number, I'm going to start them over here. Designate the size of the orbital. So I'm going to put 1 here, 2 here, 3 here, and then 4 here. There's also 5 and 6 and 7, but we're only going to go up to 4 to illustrate everything. So the lower the number, the lower the energy. So we're going to hit 1, 2, 3, 4. The angular momentum quantum number describes the shape of the atomic orbital. So this is L. It goes from 0 to n minus 1. So when n is 1, what is L going to be? 0. When n is 2, what is L going to be? Well, it's going to be 0. And what's the next number? 1. Right? That's n minus 1. For 3, we're going to have 0, 1, 2.
Okay, you lost me with the zeros.
It goes from 0 to n minus 1.
I got you. Okay.
Okay, so n is 1, it goes from 0 to, what's n minus 1?
0.
0, so it goes from 0 to 0.
Okay.
From 2, it starts at 0 and it goes to 2 minus 1, so it goes to 1. From 0, 1. For 3, the top number would be 3 minus 1, 2, so it goes 0, 1, 2. For 4, n minus 1 is 3, so it's got to go 0, 1, 2, and 3. Now you see these letters, S, P, D, and F. What are they? They're the first letters of German words that describe the shape of the orbital. So if you see L as 0, we call that S. So you can see here's an S, here's an S, here's an S, here's an S. L is 1, we call that P. Here's a P, here's a P, here's a P. L is 2, we call that D. This is D, this is D, and if L is 3, we have F. So you notice we have 1S, We have a 2s, a 3s, a 4s. These are all zeros. Now p's, we don't have a 1p. P start at 2, so we have a 2p, a 3p, a 4p. D's start at 3. 3d, 4d, and F start at 4.
Wait, what? Isn't P 1, D 2, and F 3?
Yeah, so which is the first one that has an F? Which was the first one that has a 3? Number 4. There's no 3 here, so there's no F there. So there's 2 of our quantum numbers. So a collection of orbitals with the same value of n, this is it's called a shell. You may have heard it. These are called subshells. So if I talk about 2s and 2p, the 2 refers to the quantum number, the s and p refers to the subshells. So you can think of the 2 orbital as being subdivided into an s and a p. The magnetic quantum number m sub L goes from minus L to 0 to plus L. So when L is 0, what's m sub L going to be? Well, what's minus 0? Yeah, it's going to be 0. When L is, so for 2 here we have a 0, right? 2s, so this is going to be 0. Well, 2p is 1, so what is m sub L going to be? Negative 1, 0, positive 1. So we come up here to 3, here we have an s, so that's 0. Here we have a 3p, minus 1, 0, plus 1, but here we have a d. So now we're going to have negative 2, negative 1, 0, plus 1, plus 2. Now we're at 4, we have a 0, so that's 0. We have a p, so that's plus 1, 0, minus 1. We have a d, so it's minus 2, minus 1, 0, plus 1, plus 2. Then we have a 3, so now we have minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So now we have, what we got? 1, 2, 3 quantum numbers. So there's a table that basically shows you what I wrote. And there's a chart that shows you maybe a little bit clearer than what I wrote. So if I look and say, what are the possible values for m sub L when the principal quantum number is 3 and the angular momentum quantum number L is 1? Well, you know, m sub L has to be minus L, 0, plus L. So if L is 1, m sub L has to be minus 1, 0, and plus 1. However, each orbital can only hold a maximum of 2 electrons. I cannot have, 2 objects cannot exist in the same space at the same time, 2 identical objects. So I have to make a discrepancy between the 2 electrons in that orbital. Well, it turns out Electrons possess a magnetic field as if they were spinning. So to specify the electron spin, we use what's called the electronic spin quantum number, m sub s. Two possible values, +1/2, -1/2. So if we're in the same orbital with opposite signs, they're called paired electrons. All right, let's talk about s orbitals. So there's s orbit in every shell. There's 1, 2, 3, 4, all have s's. They tend to be, by the Schrodinger calculation, their densities, they tend to be spherical in shape. So you can think of the 1s as being like a golf ball. So I know if it's in the electrons in the 1s, it's somewhere inside that golf ball. The 2s might be a softball around the golf ball. So the 2s electron is somewhere in there. The 3s might be a basketball around there. So it's the same shape, it's spherical, it's only larger, and the 4s might be a beach ball. But there's only one orbital. So I'm going to call the s, just I'm going to put a line here for one orbital. So here I have a 1s, here I have a 2s, here I have a 3s, and here, even though I have a 4s. So each one only has one orbital because they're s's. All right? S, 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 S. The p orbitals, +1, 0, and -1. How many numbers are those? 3. Well, it turns out there's 3 p orbitals. They look like dumbbells, one along the x, one along the y, and one along the z-axis. So everywhere I see a p, I'm going to do 3 orbitals. So there's the 2p. This is the 2s, this is the 1s, this is the 3s. This is the 3p. This is the 4s, and this is the 4p. They're all the same energy, p's. They're just oriented differently in space. So if I want to look at a p electron, I say it's somewhere in one of those dumbbells. Now the 3p dumbbells are bigger than the 2p dumbbells, just like the 2s is bigger than the 1s, but they occupy the same. Okay, so when you get to the d's, which are in the third quantum number, how many numbers? -2, -1, 0, +1, +2. 5. So we got 5 orbitals here. 1, 2, 3, 4, 5. This is the 3d. And then we got 1, 2, 3, 4, 5, 4d. F, how many numbers? 7. Okay, 7. So for F, we have 7. 1, 2, 3, 4, 5, 6, 7. That would be a 4F. And you can do all the calculations. I don't know if they show you what D's look like. There's what all the D's, the 5 D's look like. And one of them looks like a dumbbell surrounding a donut. But those are the probabilities of where you're going to find an electron. So F orbitals. We're not going to do that. Okay, let's go to F. So the energy of the orbitals, at least for hydrogen atom, is going essentially from bottom to top. 1s is lower than 2s, which is lower than 2p, which is lower than 3s, which is lower than 3p, which is 4s, which is lower than 4p, 4d, which is lower than 4f. Piece of cake. That's for hydrogen. Now things start changing when you go up. Why? There's more electrons, but what happens is we're talking about energies. So some of the electrons are attracted to the protons, right? So if I'm the proton, she's the electron, there's nothing between us, right? So there's certain attraction. Okay. Between her and me, there's nothing between us, there's a certain attraction. Between him and me, if there's nobody, there'd be a certain attraction, but wait a minute, you guys are there. So you're shielding him from me. So it starts changing. And we'll see what effect it has on there. So those are the energies. Where they're all the same, like these three orbits are the same, those are called degenerate. They all have the same energy. Doesn't have anything to do with their moles. It just means they're all the same energy. So with atoms with many electrons, we need to know their electron configuration, how the electrons are distributed in the various orbitals. And there's a set of rules. And I hesitate to say it's very simple, but when I say that, people don't know it's not. We talked about the electrostatic interactions, shielding, and different things. It causes those orbitals to split. And I kind of did that here, because we probably remember I said that 2s is equal to the 2p. But actually, when they split, the 2p is higher energy than the 2s. But notice as we go up, it's 1s low energy, then the 2s, then the 2p, then the 3s, then the 3p. Oh, wait a minute, it's not 3d, it's 4s, then the 3d. Get the higher, they start overlapping. We'll get to that in a minute, but I think there's a diagram in your book. 1s, 2sp, 3spd, 4spdf, 5spdf. Technically, theoretically, there's a G and an H, but we don't need it. 6spdf, 7spdf. And the way you connect these, you start with a slanted line. In this way. If I keep going, I don't hit anything. I go back and start again with the next one. Don't hit anything, go back to 2p, 3s, 3p, 4s, back up to 3d, 4p, oops, it's over here, 5s, then back up to 4d, 5p, 6s, I think it's 7s, no, 6s, then back up to 4f, 5d, 7s. Yes, how we're going to list them. So, the Pauli exclusion principle says no two electrons of the same atom can have the same four quantum numbers. So that's where that electron spin comes in. So one's got to spin clockwise, one's got to spin counterclockwise. So if you have two electrons in the same orbital, they have to be different spins. +1/2, -1/2. That's basically what it says. Okay, I'm going to kind of deviate from this a little bit. So I can put two electrons in an orbital. Now, the Aufbau principle says we're going to fill from the top to the bottom. Think about filling apples, putting apples in boxes. Big truck comes with apples. So I have boxes here, I have boxes up here, and I have boxes up here. Which one am I going to fill first? This one. Why? It's easy. So now it's full, I have to go to the next one. So you start filling at the bottom. So hydrogen, an electron, I'm going to put it in the bottom. 1s. Up arrow means it spins clockwise. Doesn't really matter which, by convention we usually do the up arrow first. Okay. Helium is 2 electrons. Oh, we call hydrogen. We're going to describe its electron. It's in what quantum number? 1. What subshell? S. How many electrons? 1s1. Helium, we have 2 electrons. Well, I can put 2 in an orbital, right? So I can put another one here. But it can't be spin the same direction, right? Pauli exclusion. So it's a down arrow. So helium is quantum number 1, subshell S, 2 electrons. Okay. If I look at lithium, it has 3 electrons. If I put the first one here, the second one here, where do I put the third one? I got to go up because this box is full. So it goes into 2s. So for lithium, if I describe all their electrons, I have the 1s, it has 2 in it, and then the 2s has 1 in it. Okay. So I'm going to skip up a little bit here. Carbon, we have 6 electrons. So again, we start at the bottom, 1, 2, 3, 4, right? So now the 2s is full, I have to move up to the 2p. So there's 4, here's 5. Where do I put 6? Do I put it here, or do I put it here, or here?
The next one is
What?
the next one.
Why?
Sounded good.
Sounded good. Okay, you're right, but it sounded good. This goes into Hund's rule. So let's say you have 3 boxes. Okay? Your job is to stuff the cats into the box. These cats don't like each other. So you take the first cat, you throw it in the first box. That's what we did there. Now you got a second cat. You got a choice. I can either try to force it into the first box, the cat will come out all scratched, or I can take another empty box.
Or do one.
Take the empty box. So the second one goes here. So for carbon, if I give its electron configuration, I say, well, I got 1s, I have 2 electrons. The 2s, I have 2 electrons. The 2p, I have 2 electrons. Okay. So let's go to oxygen. 8 electrons, so we have 6. So I'm going to add 2 more. Here's 7, right? Because I don't want to force it in with another cat, so to speak. So I got 7. Now the 8th one, I don't have a choice. I got to pair it.
Why can't you move up?
Because this is lower energy than this. Hmm? And they're not full. I still have room in the...
So you can like combine 2 different things but not the same thing in each little,
Yeah, it's gotta be an up arrow and a down arrow.
okay.
Can't have two up arrows or two down arrows in an orbital. So if I do oxygen, it would be 1s, 2, 2s, 2, 2p, 4. 8 electrons, superscripts add up to 8. So let's just look at this overall. Every time I have an s orbital, how many electrons can I put in? 2. So I can put in 2. Here I can put in 2. Every time I have a p, how many can I put in? 6. Right? There's 2, 4, 2 in each of these. So here I have an s, so there's 2. Here I have a p, is a 6. How many can I put in a d? 10. So here I have 2, 6, 10. How many can I put in an f? 14. So in quantum level 1, I can have a total of 2 electrons. In quantum level 2, I have a total of 8. Quantum level 3, 18. And 4, 24, and 8, 32. And remember we said as the quantum levels they get bigger. So I can put more electrons in there. So every time I see an S, I know the maximum I can put in is a, every time I say P, the maximum I can put in is a, no, a P, 6, a D, 10, F, 14. I'm kind of shortcutting this whole slide presentation, but so now we have that map on how to fill them up. And let's okay, talked about the Aufbau principle. You go from bottom to top, and then Hund's rule. You don't pair them till you have to. Okay. So general rules for writing electron configurations. Start with the lowest number first. Okay. Each orbital can accommodate a maximum of 2 electrons. They will not pair into degenerate orbitals if an empty orbital is available, which means you don't pair them if there's an empty box. And the following figure, which is what I wrote, 6p, 7s, right? 6p, 7s, okay. So let's do let's try chlorine. How many electrons in chlorine? Guess I'm really not mean?
Should
No, you shouldn't. 17. So I'm going to start. What's my first? Which S? What's it say? 1. S. How many can I put in S? Okay, that's done. Now what's the next one? L. Follow the line. 2S. How many can I put in yes? 2. What's next? Which P? Or not 2P? All right, so how many can I put in the P? 6. How many have I used so far? 10. So I'm at the 2P, where do I go next? 3S. How many can I put in there? What's after the 3S? How many did I put in there? Down. 5. I only have 17. You can put in 6, but I only have 5. So it adds up to 17.
I'll say that now.
I told you it wasn't bad.
Until you get like,
We're gonna have to do like compounds.
Germanium?
well, there's something.
No, you don't do compounds. So what is germanium? Go ahead. What number?
32.
32. You would pick one with 32, okay. 32. Let's start.
Okay, sometimes you use other elements like don't use, don't do it.
Do it with weight.
Okay.
Okay.
Not good.
Yeah, do it. Tell me. Start. What comes after 3Ps?
Oh, we got it in 3 feet. Oh,
Yeah.
we got 4 extra.
How many?
2.
So I keep track of, see, there's 10, there's 20, up to here we've got 20. What comes after 4S?
3D.
3D.
Why don't you do 3D?
First, follow the line. 3P, 4S. Go back up, now you do 3D.
Oh.
How many? 10.
Correct, that's it. 32.
Now we're at 30.
Okay,
4P what? 4P2. There you go.
I had them in this little bit.
Okay. We'll stop the lecture here because I'm not going to stop. I'm going to pause it.